Okay, starting with ionization energies. These are ionization energies are also periodic properties, which vary, predictably within the periodic table. Ionization energy is just the energy that you have to put in if you want to take away a valence electron and create a cation. And remember, whenever you remove or add an electron from or to an atom, it's always going to be a valence electron. It's practically impossible to remove core electrons without removing the valence electrons first. Technically, the atom needs to be in a gaseous state to have it conform with the ionization energies that are listed in the tables. And it also needs to be in a ground state. That is, all of the electrons are in the lowest energy positions available, which is the way you normally find atoms anyway. Anyway, there are multiple ionization energies for any given atom. The first ionization energy is the energy required to remove one valence electrons from an atom to form an ion with a charge of +1. So like for just a generic element X in the gas phase goes to X plus in the gas phase plus an electron. The delta H, or the energy for this reaction, would be the first ionization energy for element X. There's also second ionization energy, which means removing an electron from a +1 ion to form a +2 ion. And so in this case, for element X, it would be X plus yields X2 plus another electron. That would be the second, the delta H for that reaction would be the second ionization energy. And you can keep on going and going and going until you run out of electrons. So the number of ionization energies possible for an atom would be however many electrons it has. So for something like, say, I don't know, calcium could have as many as 20 ionization energies. The ionization energies tend to get bigger and bigger as you go along because, well, the first electron is the easiest to remove. Depending on what element it is and what charge it normally likes to take with ions, the second ionization energy might be good too. Like for instance, if you got magnesium, the first ionization energy is fairly low, meaning you don't have to put much energy into it to get the first electron out. And the second one is pretty low too, but bigger, because magnesium likes to form ions with a +2 charge, so it doesn't mind losing the first 2 electrons. But then if you try to take a third electron out of magnesium, whoa, that really jumps. You have to put a lot of energy in to get a third one out. So ionization energies increase as you go on and on and on, but how much they increase really depends on what element it is and what its valence shell structure is like. Basically, once you get past the valence electrons, then the ionization energy goes way up. Some of them are very high to start with. As we've already said, metals generally tend to lose electrons to gain greater stability as ions. And so ionization energies for metals are relatively low. Non-metals like to gain electrons for greater stability. And so the ionization energies for metals would be quite high to begin with. Something like fluorine does not want to give up an electron no matter what. You're really going to have a fight on your hands if you want to take an electron away from fluorine. Fluorine desperately wants to gain an electron so that it can have the same electron configuration as neon. So for something like fluorine, you get a very, very high ionization energy. For something like cesium or francium, the ionization energies would be pretty low. But in each case, it's still true that the second ionization energy is bigger than the first, and the third is bigger than the second, and so on. Ionization energies are always positive because the process of taking an electron away from an atom or an ion is endothermic. That is, you have to put energy into it, even if it's an element like cesium or francium that form cations pretty easily. You still have to put some energy in to take that electron away, or those electrons away. As a result of taking the electron away, you may gain an amount of stability that is greater than the amount of energy you had to put in, but you still have to put energy in. And so the energy you have to put in to take an electron out is independent of any stability or stabilizing energy that you might get after that process is done. Ionization energies tend to be smaller for larger atoms, which makes sense because in the larger atoms, the valence electrons are farther away from the nucleus, and there's more shielding because there are more core electrons. And so it's easier to get the valence electrons away. That's why cesium and francium have the lowest ionization energies of all, because they're at the bottom of group 1A, and so the valence electrons are fairly far away from the nucleus. They're in the 6th or 7th shell. Whereas something like lithium doesn't have a very high ionization energy, but it's higher than anything else in group 1A because the valence electron is right near the nucleus. It also tends to be, ionization energies also tend to be smaller for metals, like I said, because metals generally want to lose electrons to form cations. Nonmetals want to gain electrons, so the ionization energies are much higher for nonmetals. See, the lowest of all would be cesium and francium because they're large metals. And actually, the highest of all is not fluorine, although fluorine is very high. The highest of all is helium, because helium is a very small nonmetal. And it's one of the noble gases. It has a completely filled valence shell, which is its only shell. And that makes it very stable. It does not want to change. The overall trend generally is that ionization energy increases going up a group and going left to right, with francium being the lowest and helium actually being the highest. Okay, so we have a little example here of ranking ionization energies for a group of elements. Which of these elements would have the lowest value for ionization energy? We've got oxygen, polonium, lead, and barium. Oxygen is way up here. Polonium is down here, and there's lead, and there's barium. Well, we're talking about ionization energies, so the nonmetal oxygen would definitely not be the lowest. In fact, oxygen is the highest ionization energy in that group because it's a nonmetal and it's in the upper right corner of the periodic table. So that then the competition would be between the three metals, polonium, lead, and barium. Well, the trend goes ionization energy increases left to right, so it should decrease the other way. And you've got a metal here and a metal here and a metal way over here. So barium would be the lowest of those three. And it is indeed barium. Barium's the lowest, oxygen is the highest. Okay. The next thing is electron affinities. Electron affinity, again, is attraction for an atom for electrons in the gas phase. So we're talking about separate independent atoms here. We're not talking about atoms involved in a bond. And so the more they attract electrons, the higher their electron affinity. It's kind of similar in concept to electronegativity, which we will go over in more detail in the next chapter. Electronegativity is the attraction for an atom for electrons within a bond. And although they're similar concepts, the trends are not totally the same, as we'll see in a moment. The energy, electron affinity is basically the energy change for the process in which an atom or ion in the gas phase gains a valence electron and forms an anion, or a lower charged ion, or a more negatively charged ion. So element X in the gas phase gains an electron and forms the X minus ion in the gas phase. The delta H, or the change in energy for that reaction, would be the electron affinity for element X. As with ionization energies, there are multiple electron affinities for a given element. You could then take X minus and add another electron to form X minus 2 ion. and that would be EA2, or the second electron affinity for element X, and so on and so on and so on. The values are generally, the values are negative or more negative for nonmetals and more positive or endothermic for metals. And that makes sense because generally exothermic is associated with being spontaneous, and it's the nonmetals who want to gain electrons, whereas endothermicity, if you like, is associated with non-spontaneity. That is, you have to put energy in to make it happen, and that would be associated with the metals because metals don't want to gain electrons; they want to lose electrons. So it makes sense that you'd have to put energy in to get an electron, or to get a metal to accept another electron. There's an exception, group 1A. For some reason, they are exothermic. I'm not really sure why when you add an electron to them. I guess it's they could be exothermic because for group 1A, of course, they have one electron in the s orbital of the valence shell. And I would guess that the reason that the electron affinities for them are somewhat exothermic would be because adding one more electron will basically fill up the valence shell. So lithium, if lithium has the electron configuration 1s2, 2s1, that is, the s orbital in the second shell is half filled. If you add one more electron, then it has 4 electrons like beryllium, and that would be 1s2, 2s2, which means that the valence shell is now completely filled, and that would result in a certain amount of stability. So actually, you can get the alkali metals to accept one additional electron. The trends are generally, the values become more positive to the down, to the left and down, and they become more negative up and to the right, except for the noble gases. Noble gases are happy as they are. They don't want to gain electrons and they don't want to lose electrons. And this is a very general trend. There are a lot of exceptions to these trends. Figure 635 on page 330 or 340 will basically shows you that. And electronegativity, which again is going to come up in the next chapter, is a measure of the attraction of an element for electrons within a bond. And that is very useful in a lot of situations. Just determining, what type of bond you've got will often depend on the difference in electronegativities for the two elements involved in the bond. This does have electronegativity also has a much more regular and predictable trend. The trend in electronegativity is for it to increase going up a group and to the right. The least electronegative element of all is francium, although cesium is the same, actually, the same value. And the most electronegative element of all is fluorine. This is one of those trends that the noble gases don't fit into, though. So electronegativity increases up and to the right. And you can just, if you remember which one is lowest and which one is highest, that can kind of show you the trend. Francium is the lowest and fluorine is the highest. So it must increase going this way and going this way. And that is the end of the chapter for chapter 6. So let's see, that would mean the homework problems if today is Tuesday, that would mean the homework problems would be due, I'll say Friday, by the end of the day, Friday. And well, that brings us to chapter 7. Chapter 7 is a long one, but fortunately, a lot of it is review of stuff that we've already done. Some of the stuff we've already done has actually been in the book, and some of it is stuff that I have that I have mentioned along the way because I thought it was appropriate. Sorry. And so we'll hopefully be able to go fairly quickly over the first few sections of the chapter and get those out of the way because, like I said, there's stuff that we've heard before. Chapter 7 is about chemical bonding and molecular geometry. Chemical bonding is important because it's what creates molecules. And most of what we deal with in chemistry and most of what we deal with in everyday life is made up of molecules or compounds of some sort. And they wouldn't exist if bonds didn't exist. And a lot of the properties of that compounds or molecules have will be based on the type of bonds involved in holding together the elements that make up those compounds. So understanding the bonding can be very important to understanding the compounds. Molecular geometry is also very important because it's about the shapes of the molecules, and the shapes of the molecules control a lot of things like chemical properties and also physical properties. Things like solubility is controlled largely by somewhat by chemical bonding, but also by the molecular shape, and also function. For a lot of biomolecules like the proteins and enzymes in our bodies, their function is intimately involved in their shape. And if anything happens to change the shape of the molecule, the function will change, or it'll just stop functioning at all. And that can be a very bad thing. Molecular geometry is also very important in drug design because a lot of drugs are made specifically to interact with some of these molecules like proteins and enzymes, which have specific shapes, and therefore any molecule that interacts with them has to have a specific shape. So in order to design a drug that's going to have the desired effect, you have to understand the shape of the molecule you want it to interact with. Okay, so bonding helps determine things like polarity of molecules, and polarity of molecules helps also determine the level or strength of intermolecular attractions. The intermolecular attractions are what determine whether something is going to be a solid, liquid, or a gas. And so without bonds, everything would be just separate atoms. And atoms are nonpolar, meaning that they generally have no attraction for each other. And so solids and liquids basically wouldn't even exist if it weren't for chemical bonds. Sorry, excuse me. Even elements that are liquids, like say bromine. Bromine is a diatomic element, so bromine atoms actually have a bond with another bromine atom. That's a bond. So, and it's the size of the molecule that allows it to condense into a liquid. Metals exist mostly as solids, except for mercury, which is a liquid. But metals exist as solids in a situation where they have what's known as metallic bonds holding them together. That's a form of bond. So if it weren't for bonds, metals would just be separate atoms. And essentially nothing would exist other than just a bunch of separate atoms. So polarity of the molecules and the intermolecular attractions determine whether something is a solid or a liquid or a gas. That kind of thing will also determine melting point and boiling point. Polarity and intermolecular attractions will determine whether it's soluble in water or not. And also, reactivity and function, like I said, especially biomolecules like proteins and enzymes. The first section is about ionic bonding. We've already done quite a bit on ionic bonding. So again, I'm going to move through this fairly quickly. An ion can be thought of, again, as basically an atom or a molecule. That is, monatomic ions would be like an atom with an electrical charge, whereas atoms by definition do not have electrical charges, but if it does have an electrical charge, then it's a monatomic ion. If a molecule also by definition has no electrical charge, but if a molecule that is a group of atoms bonded together does have an electrical charge, then it's known as a polyatomic ion. So an ion is basically just an atom or a molecule with an electrical charge. And that charge is due to a gain or loss or gain of valence electrons. And normally you'll form an ion only by gaining or losing valence electrons. and nothing else. No core electrons will come or go, just valence electrons. Loss of an electron or one or more electrons gives you a positive ion or a cation. Gain of one or more electrons will give you a negative ion or anion. Ionic compounds are made up of ions. Duh, makes sense. And ionic compounds usually involve a metal and one or more nonmetals, or polyatomic ions. So for instance, sodium chloride is a classic example of an ionic compound. It involves the metal sodium and the nonmetal chlorine. So you see sodium's way over here, that's a metal. Chlorine is way over here, that's a nonmetal. If you see a metal and a nonmetal together, it's a pretty good bet that it's an ionic compound. An example of an ionic compound that doesn't contain any metals, though, would be something like ammonium nitrate. If you remember the polyatomic ions from when we were going over them, and if not, you can look back at the list. The ammonium ion has a +1 charge, and the nitrate ion, the NO3, has a -1 charge, so they will fit together in a 1-to-1 ratio and make the compound ammonium nitrate. And that is an ionic compound, even though there are no metals in it, because it's made up of polyatomic ions. Also remember that polyatomic ions have ionic bonds between themselves and other ions, but the bonds within a polyatomic ion are covalent bonds. So for the ammonium ion, the bond between the ammonium ion and the nitrate ion will be ionic, but the bonds between the nitrogen and the hydrogen will be covalent. And the bonds between the nitrogen and the oxygen and the nitrate ion, those will be covalent. But between ammonium and nitrate, it's an ionic bond. And so ionic compounds are held together by ionic bonds. And again, that makes sense. The attraction there is an electrostatic attraction because one ion has a positive charge and the other has a negative charge. And positive and negative attract each other, just like the north and south poles of magnets attract each other. So normally what will happen in an ionic compound is the metal will lose valence electrons to form a cation. If it's a main group metal, it'll lose its entire valence shell to form a cation. If it's transition metal, then it's more complicated. And the nonmetal will gain valence electrons to form an anion. And because positive and negative attract, that attraction between the two is the ionic bond. It's important to keep in mind, though, as we saw before, but I want to emphasize it again, that ionic bonds are three-dimensional. And so that is, an ionic solid doesn't exist as separate individual molecules. So there's no such thing as a single molecule of NaCl. The Na ion is attracted to Cl ions all around it in 3 dimensions, above, below, left, right, front, and back. And same with the Cl ion. The Cl- ion is attracted to Na plus ions all around it, above and below and to the left and to the right in 3 dimensions. And we call it NaCl because the overall ratio is 1-to-1. For ionic compounds, the formula we cite is the empirical formula for the compound. If you have a chunk of sodium chloride, even if it's just one little individual grain of sodium chloride, that grain of sodium chloride will contain literally trillions and trillions of sodium ions and trillions of chloride ions. But when it all comes right down to it, whatever number of sodium ions it has, it will have the same number of chloride ions. And so it's always a 1-to-1 ratio. And that's why we call it sodium chloride, NaCl. And there's a good diagram in the book that shows the structure of something like sodium chloride. It's a 3-dimensional network of alternating positive and negative ions. And again, we just call it NaCl because that's the lowest whole number ratio of positive ions to negative ions. Ionic compounds are normally crystalline. Crystalline just means that it has a long-range, 3-dimensional, regular repeating order for the arrangement of the ions. And sodium chloride is a good example of that. It's alternating sodium Na plus, Cl minus, Na plus, Cl minus, on and on and on in 3 dimensions. And that is a regular repeating order. It's not a case where you just throw the ions in any old way, and you might find a spot where there are a bunch of Cl minus ions clustered together, and some other spot where you might have a bunch of Na ions clustered together. You won't find that. It will always be alternating Na plus, Cl minus, Na plus, Cl minus. And most ionic compounds are like that. And because of this crystalline structure, they have certain characteristics. For one thing, you'll notice if you look at sodium, little grains of salt under a magnifying glass, you'll notice that they tend to be more or less cubic. And that's because when you break up sodium chloride, the structure tends to fracture along the planes between one level of ions and the next one down. And so you tend to get flat surfaces and square corners. And also because of the crystalline structures are very rigid. The ions are fixed in place. And that means that ionic compounds are solids at room temperature. They have very high melting points and extremely high boiling points. Many are soluble in water, and that's because water is a polar molecule, and that is the molecule has a negative end where most of the electrons settle, and it has a positive end, which is generally lacking in electrons. And this diagram will make more sense as we get to covalently bonded compounds a little later. But anyway, the lowercase Greek letter delta is used to indicate a partial charge. So when I say like delta plus, that just means a partial positive charge. It's not a full +1. It's maybe plus 0.6. I don't know, something like that. It's not a full +1. And a partial negative end, which would be maybe like minus 0.6, but not a full -1. But anyway, water is polar enough that the partial positive charge can be attracted to negative ions, and the partial negative charged end can be attracted to positive ions. And so many ionic compounds are soluble in water because water is polar, and ionic is kind of like a form of being superpolar. And basically like dissolves like. So polar things like to dissolve in other polar things. Things that are not polar tend to dissolve in liquids that are not polar, like wax will dissolve in gasoline, that kind of thing. So they're brittle and rigid. If you hit them with a hammer, they don't squash out like metals do. They shatter along the crystal planes. And again, that's why grains of salt are little cubes. The ionic bonds are very strong, and that's what makes them brittle and rigid, actually. They're poor conductors of electricity as solids because the ions can't move around, but they're good conductors as molten liquids or when dissolved in water, because then the ions can move around, and the ions are electrically charged, and that can have the effect of carrying an electric current. Properties of atoms and ions are very different. So sodium metal versus sodium ions, that's very, very different. Sodium metal is a soft, relatively soft metal. You could cut it with a butter knife, and it reacts very violently with moisture, versus sodium ions, which are perfectly happy dissolved in water, and we can eat them with no ill effects. And chlorine as an element with no electrical charge is kind of a pale yellowish green gas. It is very corrosive. It's deadly to inhale. In fact, the very first chemical weapon in wartime was just plain old chlorine gas because it burns, basically it burns your lungs out. If you've ever taken the lid off some a container of pool chlorine and gotten a good whiff of it in your face, that's basically chlorine gas. Because pool chlorine is actually, it comes in solid tablets. It's actually sodium hypochlorite, which is actually like concentrated bleach, but it's sodium hypochlorite is an unstable compound, and it breaks down to give off chlorine gas. So that whiff of nasty stuff you get when you take the lid off, that's chlorine gas. Versus chloride ions, which again are perfectly happy dissolved in water. They're perfectly stable, and in fact, sodium chloride, the compound, is necessary for us to stay alive, at least in small amounts. So it's quite different from the elements that make it up. And the ions, again, form because their electron configuration makes them more stable. Cl minus, when chlorine gains 1 electrons, it has 18 electrons instead of 17, which means it has the same electron configuration as argon, which makes it much more stable. So Cl minus ions are much more stable than chlorine atoms. Sodium has 11 electrons of its own. When it loses an electron to become Na+, it has 10 electrons, just like neon, which again makes it much more stable. So Na+ ions are much more stable than Na or sodium atoms. And that's basically why the ions form in the first place, because the ions are more stable than the neutral atoms. Okay, so that brings us to the end, I think, of part B. Yeah, we're a little over time, so I will cut it there, and we'll come back with formation of ionic compounds in just a moment.